Very well. Welcome. Thank you so much for joining us on a Friday afternoon for the very first of the seminars in the sales series. Today we have Dr. Shayok Mukhopadhyay. He's just joined us as an associate professor of electrical and computer engineering. Shayok received his PhD in computer and electrical engineering from Georgia Tech and is a leading expert in robotics, control systems, renewable energy, and battery modeling. He has received prestigious awards, including the Best Presentation Award at the American Control Conference. Shayok's contributions extend to leadership roles within IEEE, where he served as chair of the IEEE UAE section, CSS, RAS, EMES joint chapter from 2022 to 2023. His expertise and accomplishments greatly benefit his academic department and the field of electrical and computer engineering. One of the many wonderful things that Shayok is doing is advising the robotics club, and he is also involved in teaching the robotics autonomous robots course. And we are very excited to learn from his expertise today and in the coming. Please welcome Shayok.
Thank you, Aid, for the nice introduction. Welcome to all of you, and thank you for joining on a Friday evening, afternoon. And so, without further ado, this is my talk. The area is generally more into the control aspects, but some of it is tied to robotics. You will see it. And as Mohit mentioned, I am looking after the robotics club here. So if you are interested in any robotics related activities, autonomous driving, please come and talk about some projects into them. All right. So going forward, technical issues. Let's see. My computer is unresponsive. There we go. Slide one. Are we on slide one? Yes, we are. Is there a way to get rid of this? There. Yes. Okay. So here is the motivation related to variant sets. So this is from 2011, back when I was a PhD student, and this is from Grand Isle, Louisiana. And we were down there, quite a few of us, around maybe 15 or 20 of us, two different teams, my professor and other professors. And we had two of these vehicles you can see on the left. The lower one is called the Fetch. This was from another professor's team, Dr. Mark Patterson. And the one above, this is what our team developed. This was an autonomous boat that we had developed. And of course, I was dealing with the autonomy aspects of it, how to make them basically drive on the water by themselves. Okay. So what were we doing down there in Grand Isle, Louisiana, in the Gulf of Mexico in the summer of 2011? It was exactly around 1 year after, if you remember, the Deepwater Horizon oil spill that had happened in the summer of 2010, April 2010. And so we were down there trying to survey the coastal lagoons, and we had to do automated surveys because you have to cover a lot of distance, and we wanted to figure out how much oil there was still left over after whatever BP had done. BP was literally down there washing beaches, and they didn't like that we were there to do the measurements. We were literally hauled up into a haven somewhere and asked exactly what we are going to say or what we're going to do, but we were there to do our stuff anyway. So here we are, and these are some of the results. If you see on the middle graph, this is with ASV Victoria, it was named, our little boat. We are trying to follow this line autonomously, and our boat's doing somewhat okay. Sometimes, it loses GPS track, or maybe it's affected by the current. It does these little loops, and the current itself keeps going, right? Then here is another one. This was overlaid on a map, but it is zoomed in. We are trying to maintain a circular curve around a point, and what I want to draw attention to it is, this is an autonomous test, but what I want to draw attention to it is, you can clearly say that we are kind of successful in maintaining a circles or circular shape of a certain size, but this is the center, so we are clearly offset. Okay, and that's because of the water currents on bending. Had it been a different current, we would have achieved a different configuration of it to the center, but it would have been somewhat of a similar shape, right? So when I say an invariant set, my example is this. Essentially, I'm trying to solve the problem of if I put that boat, one of these boats, in water, and I turn it on and I try to make it do a mission, follow a path, how far will it drift away from that mission? Okay. And in the worst case, let's say if I lose power, I have to operate at half power and I have a certain water current going, then what is the area in which my boat will stay contained? Because if I know this, then I can have some hope of recovering. Otherwise, it's just not, it's going to go wash out to sea at some point. Okay. And why is this important? Especially on a road vehicle, when you're doing autonomous driving, if something goes wrong, you can maybe manually drive it back, or it's stuck on the road, it's easier to handle. In these scenarios, I'm not joking. In one of the days, we put the boat in water. We had tested it the day before. Everything was fine. We put the boat in water, and it literally stayed where we put it. It didn't move. But the systems also showing that everything was operational. Everything was running. In fact, we could hear the motors running. So we later realized that the currents were such that they were exactly equal and opposite to the thrust that the boat was producing. So it was therefore not going anywhere. So how do you solve this problem, or how do you try to estimate that area where the boat will stay in? This is what I mean by an invariant set. So in the context of curve tracking, if you formulate in a particular way, I haven't put the formulation up here yet, the entire formulation, but what it boils down to is those two differential equations that you have on here. Rho is the perpendicular distance of your robot or autonomous vehicle from a curve that it is trying to track. Okay, so it's shadow on the curve that it's trying to track. And phi is the orientation with respect to the tangent drawn on that curve at that point, right? So what you would like to do is maintain rho at a certain rho naught. That would be the minimum distance away from the curve that you want to get. Otherwise, you will maybe hit the curve. Maybe you will hit a sidewalk when you're talking about autonomous driving. And phi, of course, has to be 0 because you want to be parallel to your curve, right? So that's what we are trying to do. And the question asked is, what is the size of the smallest set centered around the equilibrium point of this system of differential equations, in which rho and phi will stay for all time given any bounded disturbance? Here, the disturbance is only entering in the angle, but you can also add it here if you want. So given any bounded disturbance, you don't know the functional form of the disturbance. You don't know what that function is going to look like. But from your tests, it's usually easy to guarantee that it's going to be bounded in a certain range. For example, from literal measurements or from weather data, we knew that the currents cannot be imposing force in certain directions more than a certain amount of force. So we know that. So at least we can have the bound of the disturbance. All right. So how is this problem solved? By the way, this is a giant open problem in the area of control. It's called computing the basin of attraction around the equilibrium point, or the invariant set estimation, largest, smallest. This has been open for, if I'm not mistaken, hundreds of years, and it will still stay open for hundreds of years, because I don't think there's ever going to be, this is the solution and that's what you do. This is, that big space to play in. So what has been done in the past? In the past, many people have tried to analytically find solutions. Those you can only find for very simple dynamics, right? Then you can write a curve that you want to impose, let's say, as a boundary. You choose a shape and you try to solve many partial differential equations, and this is called domain of attraction estimation. Or the most popular way, one of the most popular ways is, when you talk about nonlinear system stability around equilibrium points, the usual approach is you need to find something known as a Lyapunov function. A Lyapunov function is a bowl-shaped function, which you make it sit at the equilibrium point. In the case of these equations, it will be rho naught and 0 for these two. That will be the equilibrium point. And the bowl, you want to have a function which is growing outwards as you move away from the equilibrium points. And then if you are successfully able to find such a function such that the gradient on the surface of this bowl along the solutions of your system, they have to point downwards. If they are pointing downwards, then you're stable. Of course, if you have a disturbance, that's not going to point downwards always. And what we are trying to find is at what cross section, if you just cut this, Lyapunov bowl here, if you cut it parallel to the x1, x2 plane, you get what is called a level surface. And so a popular way to calculate this invariant set is, at what height should I make that cut? So I am stuck in that level set forever in the Lyapunov function. Okay, that's how you can imagine. And there are advantages to this. There are known ways to, even now, it's quite hard to pick a function that's a Lyapunov function. That is part of the art of being in control, if you say. It's less science and more art. But there are also programmatic ways to now compute these functions, right? And the problem with picking the level sets of Lyapunov functions as invariant sets is the following. If you want to calculate the smallest set or the smallest region in which my boat is going to stay in, you are trying to estimate the shape of the set and the size. But if you assume a Lyapunov function and then you make that cut and then you try to find the invariant set as a level set of the Lyapunov function, then you are de facto imposing a shape, and then you are trying to squeeze that shape as small as possible, and then you are hoping that that's going to be the best estimate. And that's not necessarily the case, right? So which is my main problem with those sorts of approaches? These are called sum of squares and relaxations approaches. You always get smooth curves with rounded shapes, but what if my invariant set doesn't have smooth curves? When I have a spiky set, then what? What happens? So what I came up with, I was thinking about this for a while, and this is purely because of, in my lab mates, we had a group and we used to have seminars like this and we used to present our work. And one of my lab mates was at the moment looking deeply into path planning algorithms. So I kept hearing him for weeks and weeks and weeks and weeks. And then somehow my ideas got morphed into using, well, why not use path planning for this? Okay, so the concepts, some concepts that I will put forth is as follows. Here's what I'm trying to do. There is x bar is my equilibrium point. Around that, I'm trying to look for the smallest variant set. I start with some big dashed boundary. That's clearly a suboptimal set. Okay, I want it to be the smallest. And what we call it as the smallest RFIS. We call it a robust forward invariant set. That's because you have disturbances to take into account. That's just nomenclature. But maybe the big box is my initial guess. Then if I try to solve the problem, I come up with this weird shaped set inside with dashed lines, and that's a suboptimal solution at that point. And maybe you iterate over it and you get closer and closer and closer. The fine dotted boundary, maybe that is the actual smallest RFIS. Okay. But maybe programmatically, you can only get to this one with the solid line, because what I am proposing is a computational approach. So my grid is never going to get fine enough to be able to approximate that. Visually, it may look like it, but if you talk to a mathematician, they will always tell you, but oh, by the way, if I reduce the resolution further, maybe I can go smooth. Okay, that's the point I'm trying to make. So now here I'm defining a curve because I'm going to be looking for the boundary of the set. So this curve is going to be my boundary. And at a point x on the curve, nx is my inward pointing sort of normal vector to the tangent. So here's the tangent, and there is nx pointing inside, okay, inside the area enclosed by the curve. And these vectors v1, v2, v3, they are from my vector field. That means they are from these, I'll go back a slide, they are generated by the right-hand side of these two equations. So whatever vector that gives me at a point in space and time is v1, v2, v3. As of course, space is fixed because you are considering that particular point in space. So if you now vary time forward, okay, depending upon what the disturbance is doing, you will get different vectors, v1, v2. Okay. Now, if you keep running your equations for a sufficient amount of time, you will get a bunch of these vectors, and you can find their extreme rays of that little convex cone. And you can now calculate what is the worst case angle between those extreme rays. And that's what I am calling alpha. Okay, so alpha is the cosine of the angles, and I'm wanting to calculate that. Yes.
Are V1, V2, and V3 three cardinal vectors in 3 dimensions, or
No, they are just, if you imagine, so the right hand side of these two equations is going to, if you write it as a 2 by 1 vector, they are just representing what are those vectors taking a value, and you can plot them as a vector field. So how they look at a particular point X. Okay, so this is what we do in control theory, in state space, whatever is on the right hand side, we call that the vector field, and at different points we try to plot that vector. That's one.
so at any given point in time, given a disturbance or even without a disturbance, are we going to have 3 vectors, V1, V2, V3, or just
No, you could have any number. This is just an example. Right. Okay. You could have, in fact, if that disturbance, the amount of time span that you're scanning, and depending upon how much you are discretizing that time span, you could get as many vectors as you want. Right. So the point is, you need enough vectors to be able to find those extreme rays so that you can calculate that worst case angle. All right. And the way you have to imagine this picture is, this curve is going to circle around and complete itself. Okay. And I want these angles to be pointing inside. I do not want these vectors to be pointing outside. Okay. Because if they are pointing outside, then a particle on the boundary would leave that curve. It would not come inside if it's affected by that force. If they keep pointing inwards, then if you solve that differential equation with these vectors pointing inwards, then you go inside. Okay, so the way we develop this as an invariance condition is called, the worst case that you can allow is that here, with respect to the tangent, these vectors are at the most allowed to be parallel to the tangent. They cannot point this way. Okay, pointing this way is bad, right? So which means I have to maintain the angle between, with respect to the normal, the angle has to be plus or minus 90 degrees, and that means the cosine has to be between, cosine of the angle has to be between 0 and 1. Okay, all right. So what did I think of after this? I wanted to discretize my computation, so I overlaid a radial grid onto it. This is my radial grid. I'm calling these A's, A1, A2, AN. I'm calling these as segment sets. Okay. And then these are further, these individual segments or rays are further discretized, and there are different points in between. I am naming them. All right. And then I am embedding a graph onto this where every point is joined to every other point except the equilibrium. Okay. Why do I want to do this? My hope is the following. My hope is I pick one of these points and then I calculate which is the next point I have to go to. And I keep doing that and join enough so that I can have a curve. But the curve has to be such that the length of that curve, or the arc length, the periphery of that curve, has the smallest sum total cost. And this angle at every point on that curve, the cosine of that angle, is 0 at the worst. Okay. Because then I have found the smallest set such that, or the smallest periphery of the set, such that at all points on the boundary of that curve, the vector field points inwards, so nothing can escape. Okay, that's the game we are playing here, right? So how do you do this? Well, this is just writing all of that I talked about with the picture. This is just writing all of this via mathematical notation. So it is pi minus 1k to pij. So if you are at a point pi minus 1k and you are going to pij, then you calculate, this is the segment, let's say this little blue segment, then you calculate the normal vector with respect to that. So literally turn it counterclockwise by 90 degrees. That's the vector n. Then you take the inner product of that with respect to a vector from your system vector field, we call it V. And then you execute this computation, which literally, if you're familiar with this kind of notation, it gives you the cosine of the angle, right? And then I have to find a point P or a vector V such that this is minimized. So the angle is minimized. So I'm finding the extreme ray. Then I take that extreme ray and I pass it into, or this extreme ray, I pass it into this alpha, which gives me what is the angle or cosine of the angle corresponding to that extreme ray. Then I take this further and compute a stage cost for navigation, is what I call it. It's given by this function C. This is simply operating on this alpha, which is the cosine, and passing it to a function called eta. What does the function eta do? It lets the angle be as is, or the cosine be as is, as long as whatever is passed in is in the range of 0 to 1, which is the good range of cosine that I want. If anything is in the range -1 to 0, that means my vectors are pointing outside the curve, right? Yeah, I don't want this. Then I pick a arbitrary number g tilde that I assign to this, and that becomes my cost, plus however far I am from the equilibrium point x bar itself, because if I move these points closer to the equilibrium, naturally the periphery should shrink down. That's what I'm thinking. All right. So what the good thing about this is, once you formulate this as a stage cost function, that means cost to go one hop, cost to go from one point to the other, this neatly ties into the path planning framework, and I'm pretty much free to use any path planning algorithm I want at this point, all right? And I was able to show that if you pick this g tilde large enough, if you make it an arbitrary large number, there is a lower bound, but if g tilde is above that lower bound, then you can make your A star algorithm pick points such that that invariance condition that I said, that the worst case I want is to be tangential, that is not violent, and you can use. Okay, it's quite a simple proof as it turns out, but you can use. So that said, then the next task is simply I take this cost functions. I also throw with it another heuristic cost function for the cost to reach the goal if you want, and then I have to plan a circular path starting from any set A0, going back to it, but I have to do it in two parts because A star does not like to start working if the goal and goal set or the time and the source set are the same. So you have to break the circular path into two halves and you plan this and you keep doing this iteratively. And then if everything goes right, you converge to the boundary of this one set. Okay. So this is what we are playing at, and I'll show you the results of how this worked out. So this is the first result with a sinusoidal disturbance I started with, and this is for the same two equations that I showed you, a set of equations. So this is the whole state space. Of course, you have to know where the initial set is. What is this blue box where you want to start to search? So I keep it around the equilibrium point 1 and 0. That's my point. And the pink curve with asterisks on the boundary, that is the set that my algorithm converges to. And if you notice what's happening to the solutions, if I solve those two equations and I plot the solutions, they are sort of circling in it. And once they enter this, this little set inside with the asterisk marks, it never leaves, it just keeps circulating. That's exactly what I'm after. And it doesn't matter what kind of disturbance you throw at it, as long as you don't violate your own imposed bounds that you used for it to calculate. So I'm trying some other function. This is just a I think uniformly distributed random variable that I threw in as a disturbance, but within those same bounds that I used for the computation. And so it all with the sound, right? So this is related to invariant sets. And why do we care about this? We care about this because for complicated systems, when you talk about model predictive control of autonomous vehicles or for drone flights, the controllers can sometimes be synthesized numerically, and their performance is also sometimes tested numerically. And it's very hard to come up with theoretical or analytical guarantees. To do the derivation sometimes it's very, very complicated. So what people look for is, if I have that gigantic set of differential equations that I know is a model of my system, then around the equilibrium point, what is the smallest set in which such a controlled system for a drone or an autonomous vehicle, what is that set in which all of the states will stay in, and that essentially becomes the exact same calculation that we're talking about. Okay, it may not be in 2 dimensions, it will be in n dimensions. That is a significantly tougher problem. With another student of mine, we have also been able to solve that, and that exists online. You can find it as a publication too. Unfortunately, I was not able to use the benefits of path planning for it. I am still thinking of ways of how to marry the n-dimensional notation with it. Maybe I will someday, but if you are interested in it, that is purely a geometrical exercise. You start with an n-dimensional, hypercube if you want, hyper surface, and then you figure out which points you want to push inwards so that you do not violate these things. That's just look into it. So tying to SAIL and the AI techniques that we are seeing nowadays, question that comes up in my mind is, what if some of these AI techniques were used to augment the data? So instead of doing a computation at every point, if I augment the data, or if I'm able to make an initial guess, where do I start at? That is always a stumbling block. If you don't know where to start, that algorithm won't work. Okay. Or what if I stuck with the path planning approach, and whatever reinforcement learning was to tell me where is the next point I go. If I train that algorithm on similar systems, will it somehow converge to the correct boundary? That's something I'm interested in finding out. I will be really interested to see what happens. Now, moving on to parameters estimation. So this is, some slide related to your first class in control. Yes.
I'm sorry for the interruption. There are a couple of questions that may be context related. So you mentioned that it's very dependent. The set of the algorithm in finding the right boundary of the Bayesian attraction depends on the initial point.
On the initial set, yes.
The initial set or initial point?
No, it's the initial set. The boundary of the initial set that you start.
But does it not also depend on the initial point from which you start?
To a lesser extent, because you can start pretty much anywhere else. So let's go back here. So the blue boundary is what you will have to choose, and you can choose wherever on that, you discretize it and you start wherever. But so that initial point doesn't matter that much, but that initial step does matter.
So you're assuming that graph is a connected graph.
Yes.
And that's something that you can impose because you are selecting.
Because I'm making the graph. Yes.
Also, was the C function that you introduced the heuristic function, or was it the cost from 1.2?
So this goes into and
someone's unmuted. You can mute them if you wish. If you go to participants.
Okay.
Yeah.
All right. Right. Okay. So what happens is the C function is actually the point-to-point cost. So if you in A star, if you recall the cost function, it is f hat equals g hat plus h hat, and g is the cost to go from one half to the next, or the cost to go from the source to where you are. So C is the g function, okay, right? And the h would be whatever heuristic cost you want to impose for going to the goal.
I'm curious, what was the heuristic function?
Very good question. The heuristic was the safest to choose is 0.
Right, so it was essentially UCS.
Yes.
Uniform cost.
Yes, because the problem is guessing what is the heuristic cost I need in this case is very hard. So if now we can somehow guess that, the advantage would be the computation gets even fast. So I would be interested even in finding that. Is there a way to now guess my heuristic cost so I can speed up computation?
And are you assuming? Are you making any assumptions about the stationarity of the underlying dynamics besides the perturbation, of course? Does the Lyapunov theorem depend on that assumption as well?
No, but if you bring into picture stationarity, that means these are deterministic systems. They are not,
So they are by definition stationary.
Yes.
Right.
Yes, but the way you could play with it is how I played with it. The cool or the neat thing is this function, the disturbance function, I injected a random uniformly distributed random number as this disturbance in here. So because the disturbance function, I don't care about the exact functional form, I only care about the bounds. I can get away with it.
Right. Sorry for the long.
No.
This is super interesting. I can't wait to hear the rest.
So going on to parameter estimation. So here I'm showing a typical first course that you take in control. Here's a PID controller. You're trying to essentially invert the system. If you choose your gains correctly, then everything converges. Your PID controller works. That's how a first class in control goes. But the important aspect to remember in these cases, you always know, or we always know in these cases, what is the value of these numbers, 2 and 5 and all these parameters. We know them. Okay, so I know the system parameters. And I also know if I generate a control signal and I plug it in as a positive signal, I know what direction I expect my output to go. Is it going to go positive or negative? I usually know this. This is called as I know the direction of my controls. Okay. So essentially, I don't expect the practical example I would give it is I don't expect that I sit in my car, it is in drive, okay, and I press the gas pedal. I do not expect it to start moving backwards. I expect it to go forward. So that's what I mean by knowing the control direction. However, there may be cases where if you write that example as a simple state-based system, then there may be cases where you do not know these A, B, and C, or it could be worse. You do not know that direction. I'm putting a plus sign here, but since I don't know B, I don't know the sign of B. So I don't know in this case, that was my autonomous vehicle. I apply a forward acceleration. Is it going to start going backwards? I don't know. Okay. So how do you do it? How do you deal with it in that case? There is a very well developed branch of literature known as null identifier based control. So I will not go into that. If you follow through the math, however, what I will tell you is you can use certain functions called as NASCON functions. These are extremely violently vibrating functions. So essentially their frequency changes continuously and their magnitude keeps increasing. The idea is, here is that function u. The idea is this function u will acquire the correct sign and the correct magnitude for the correct amount of time, so that when you plug in that u in here, this entire differential equation system will be stable and will converge. Okay, so you let this violently oscillating function do the search for you, search for the sign and the magnitude. If it acquires the sign and magnitude and stays there for long enough, things work out. And that's this mathematical definition saying what literally happens is you engineer a contradiction. The stuff on the right hand side is positive, and if you let this crazy function oscillate, like I said, then the stuff on the right hand side becomes negative, and that's not possible. Right? Things converge. Okay, that's the mathematical trick we play. So what have I used it with on energy systems? I worked with batteries for a while. So here are some ways I used it. So this is a model of an electrical circuit-based model that some researchers came up with, and there are lots of numbers in here that you need to know. You can write this down. Again, those parameters that you have, resistors and capacitors, they have certain curves, and that's what they look like. An important thing to draw attention to is the model tells you, and it's trivial to ignore or easily ignored. Maybe it's nothing, but the capacitor actually changes sign towards when the battery life is very close to almost dead. The capacitor will change polarity. This has profound effects. If you write all of those models, those equations, and the circuit, if you transfer it into a state space model, here is what you get. And you can find that there are certain stability limits. So regardless of what you are doing to the battery, okay, you have to even not take any current from it. Maybe you discharge the battery for some time and it's just sitting idle. Maybe it's self-discharging. There are limits independent of the current. They only depend upon these parameter values, such that in certain areas the battery is stable and in the other areas the battery is not stable. Okay, you can show this. And it is very counterintuitive to think about stability for something like a battery because it doesn't really go anywhere, just sits on your desk or sits in your device. But what does stability mean? Stability in this case means the following. As long as you are in the stable region, your voltage and you're discharging this, some on off discharge, the curve will look fine. The moment you transition into the unstable region, that voltage is going to drop instantaneously. And your ability to supply power is going to go away instantaneously without warning. Okay, and that's what we want to detect. How do you do it? Well, here is my argument that thresholds are not really great. If you set static capacity thresholds or voltage thresholds, you can get away with it. So for example, if I set a 90% capacity use threshold, that's this vertical line, okay? Then what happens to my voltage curves for different loads that the battery is supplying? For the black and the blue curve, I am fine. For the red curve, the voltage has dropped around 3.3 or slightly below. Most of your low voltage electronics will start complaining at that level. So it might be low already. Okay, it will shut off soon. So it doesn't work. If you set a voltage threshold, the horizontal line, for the black and the blue curve, you are fine. But for the red curve, of course, your voltage regulator, whatever, will start complaining when the voltage drops. But if you look at what's going on, you have used only about 50% capacity. And you take this battery and you keep recharging it now, the more number of times you do this, you are going to kill the battery faster. All right. So there is a cost associated to this. So essentially, if you set static thresholds, it's not good for the battery in the long term. So if we know the battery parameters, we know all those R's and C's and all the numbers, what can we do? We can design an adaptive threshold. Okay, and you can set whatever limit you want on that. You calculate a limit beta below which it's going to be unstable. So don't let your SOC or state of charge of the battery go below that. Okay, we can do that very easily. But the drawback here is I need to know all those parameters, right? And there is not necessarily a unique way to determine this. Right? So what can you do? We bring back our crazy vibrating oscillating function, the Naslon function. You can formulate something called as universal adaptive stabilizer. So you use that, you pick up the worst model that you can find, just a low pass filter, and you let this guy drive the low pass filter such that it tracks the output voltage curve of your lithium ion battery. Okay. So sort of, I take a simple model, I let this one figure out how to drive the model so that the output of this matches the real output. And it is possible to show that when the real lithium ion battery is about to become unstable, then this low pass filter is also going to be driven to instability by this. That shows. Okay. So basically, the bounded input, bounded output stability is going to fail because this input is going to skyrocket to infinity because this guy is going unstable. So without knowing those parameters, you can now detect when your battery will die, right? So this is one way, but what does this have to do with parameters estimation? You can do the tests, and these are some results. You can feel free to look at it in the publications, but this is just to say that this works out not just in math but in real life too. So what? How can this be used for parameters estimation? Well, you can turn around, before I talk about what's happening on this slide, you can turn around any controller into what is called an observer. So essentially estimating quantities, or you can also use it now to estimate parameters. So that's where I'm heading to. And so before that, what are the other ways in which people usually estimate parameters of energy systems like batteries, supercapacitors? What do they do? Here you can see one result. They do many on-off, cycling tests, many. Hundreds. Here is another one. They try to figure out, constants, time constants, slow time constant, fast time constant. But again, this is dependent upon the type of signal, the type of, excitation you apply, and you take it away, and how you're measuring it. So there are ways to make mistakes in this, errors. Or many researchers, they come up with automating systems that will do hundreds of tests. There is an entire industry right now. There are companies that build battery cycling machines, hundreds of thousands of dollars for battery testing, common. But what we thought of was, well, here is the physical lithium-ion battery. We will take that crazy vibrating signal, the universal adaptive stabilizer. We will make a model, a copy of the battery, just as we saw, with some initial guesses of the parameters. Let's say very bad initial guesses, and try to drive this by this so that it starts accurately tracking the output voltage. If you do that, and in this work, which was an initial phase, if you also tell me what is the open circuit voltage of the battery, then you can get all the parameters to converge, and you can even calculate the last bit, which is the internal resistance you can use. Okay. The only caveat is you still have to run these additional tests to find out the open circuit voltage. That can take some time. Okay. So at the end of this, when we did all of that testing, we tested it on lots of batteries, 16 batteries, and we ran lots of tests, charging tests, discharging tests. We did all of that, and the errors were fine within the limits, and numbers look nice. So it all works. And so at this point, because I've been doing this work for a while, so the previous works that I showed you, the tests needed were, if not in the hundreds, maybe in 500 tests. At this point, we are able to cut that down to, let's say, around tens of tests, 10, 15 tests. Okay. And over time, I kept working on this, and as it says, we are now able to identify all of those parameters in just one run. So using that same, universal adaptive stabilizer business, we have been able to figure out a way to estimate everything in just one extent. And that was with another one of my students. So what do you need? You just, keep making your model bigger. You figure out the open circuit voltage curve that I talked about. You try to figure out a way to write it into a differential equation form, is what we did. We copied that exact same thing into an observer. There's a gigantic observer. And then on the right is the universal adaptive stabilizer. Okay. So here it is. U equals minus NKE. N is that crazy function. You feed this in, and then you do the math, and you can figure out that all of these numbers, okay, all of these are R hats. And here you will see there are some R's. The R's are the real ones, the R hats are the estimated ones, and they will converge. And we are able to show that they will converge in just one test worth of data. In fact, we were able to get convergence in just 1.5 seconds. So you can literally deploy this in any real-time, let's say, an onboard vehicle scenario, use the parameters, and then you use it for state of health estimation. But again, nothing comes for free. The caveat again is, this is the equation that adapts the parameters and tries to settle to the estimates. Is it helps to know the lambdas, we call them as weights or confidence bounds. Okay, and it helps to know what are the upper and lower bounds of the steady state values in which the parameters will settle. So essentially, if there is an internal resistance of a battery, the battery is a device that supplies power. You know that this cannot be in kiloohms, because otherwise you will be wasting a lot of power. This has to be in milliohms, maybe less. So if you have a knowledge of this range where you are looking, then the convergence will be faster. Otherwise, it will be a slower convergence. Okay, so better ways to estimate again where to begin. What is the initial guess range? That helps again. And this is not limited only to energy systems. Once we observe this, I started trying with other systems, and here is just the diagram for it. I haven't shown you the actual experiment to this, but we were able to model parameters or estimate parameters for underwater vehicles. In this case, I asked my collaborator who was working with me, can we try to go for a very large number of parameters? Here it's 122 parameters and 2 hours of drive. It worked out. Okay, it seems like it worked out. So there is something about that function, that Nussbaum function. I don't know what that is yet. It works in these scenarios. Maybe there is something deep lurking there, but I hope to be able to find it. What is the property of this particular type of observer or that function that is making these things work? But there is something. Okay, that's all I know for now. And there is something about it that makes these things work. But again, the question is now, what if there were some techniques that were used to augment the data or to make the initial guesses? If I am after cutting down experiments, but maybe if I do run a few experiments, instead of running tens of experiments, maybe I run 3 experiments and I take the data and I ask some AI system to tell me, start here, start looking for the parameters in this boundary, and you will converge. That can be very helpful because for a system like a battery and being an electrical engineer, I know how to guess the bounds. But if I go to any other system, I may not always know how to guess the bounds. So that's where it can be useful. So with that, I think we have about 10 minutes left, and that's related to parameter estimation. And I would like to say thank you for listening.
So much, it's been wonderful talk. I have so many questions. I'm going to abuse my position as a moderator to ask some of these questions. But I'm going to give everyone else, especially those who are online, some time to ask questions as well. So for the parameter estimation formulation, if you can go back 3 slides.
Yeah. Okay.
There we go. Essentially, what you're doing is you're measuring the moment of the estimation as the square of the error,
Yes.
right? And then you're regularizing it with what you call upper and lower confidence intervals.
Yes.
And this works for the relatively, well, for us, tens of parameters are considered small.
Yeah.
Because we unfortunately have to deal with billion parameters and
Yeah.
so on. I'm curious if you looked at more conventional regularizers to, instead of looking at an upper bound and lower bound, maybe just a regularizer that tries to limit how suddenly certain parameters change with respect to others.
That's a very good suggestion. I haven't, and I am very interested in trying it. Yes.
Have you looked at Kalman filtering?
Yes. And carbon filtering, extended carbon filtering, particle filtering. And my only problem with all of those approaches is the following. To make those work, you need a model. And here I am trying to estimate the model parameters.
Kalman filtering for model adjustment. So the control is adjusting the parameters of the model.
Exactly.
Right.
And so here what we are doing is, that is my observer, which is not a carbon filter, and it is adjusting the parameters. So the problem with carbon filters is you linearize it with an extended carbon filter, you have to linearize it, and at some point you are going to be taking some inverses. Right. There are other forms which do not need inverses, and I have played around with all of those, but what I found is at some point it is either going to track the model or it's going to track the data. And then what if none of them is good enough?
You mentioned your current experiment time is 1.5 seconds.
Yes.
How many data points is that?
So this is not the, so all right, let me back. So 1.5 seconds is the convergence time, but the entire time series data that we had access to, that is on the order of, I don't know, hours. But what I'm saying is that entire hour worth of data, I didn't need to use it. The parameters had literally settled to whatever they were settling to within 1.5 seconds.
And this was done through a numerical process, right? What was the sampling resolution for that?
I think it will be milliseconds. I can check, but it is definitely not more than a millisecond. I need the current and voltage measured per millisecond.
Does this mean that you are essentially modeling the problem as a large signal problem, as opposed to a small signal problem? Because the moment of variation is small, so you can consider it a piecewise linear dynamical function.
Well, you could, and that's fine,
Oh, this is my interpretation of your observer plus estimator method.
Yes, yes. Because there is essentially, so that's the observer, and somehow, if you go back to the previous case, because here there are clearly nonlinear terms involved as well, but If you go back to previous case, then yes, you are, because the low pass filter is linear, and then the observer feeds some, time varying input into it. So yes, exactly. So the way I would like to say it is, I want the optimal fight between tracking the output and not tracking the output. And if you do it just right enough, then there is a little gray area in between where everything should work fine and your parameters should set.
Have you looked at the saddle point equilibrium or the region of balance between the two?
No, I haven't. Something to try.
This has been beautiful. I'm sorry, everyone, if I bombarded Shayok with my questions, and sorry if I bored you. Shall we open it to students' questions? As well
Sure,
as
sure.
finish? I spoke with your colleague Sachin yesterday. They showed me the implant, the drug dispenser implant. There's an implant that Medtronic has developed that is implanted in the body, and it dispenses drugs directly into the spine.
Wow.
And one of the questions that I had was, how do they deal with the stability of the battery? The reason I asked that question was the exact same thing that you mentioned. And well, I don't have an NDA with Medtronic, so I don't know how they dealt with it. But I think what you're working on finds life-saving applications.
Well, good to know. I mean, I would love to be able to use this for it.
Any questions from the audience? How about our online audience? Would you like to check the participants? We don't have any hands up, so Shayok, this was wonderful. I truly enjoyed it. I have goosebumps. That's how beautiful some of the ideas were. Thank you so much for the presentation. We really hope to keep hearing about your research in the coming months.
Sure, and just to because I want to go back to the thing you mentioned here. I don't know if you can see it here. U equals minus NK. So when the error goes down, the idea is if the error becomes zero, the controller literally disappears.
Right.
So essentially, the system is now going to track whatever it's tracking with the help of just the parameters. And if it's done that right, then the error stays zero. If it doesn't, it goes up and the controller comes into effect.
I keep trying to map this into a gradient update process.
Yes.
And I suspect you can prove that this is a consistent estimator for certain regimes, but for others,
Maybe not.
maybe may get stuck in local
Yes.
optima.
Yes. So that's exactly what I'm saying, because this family of Najman functions, it's not just one function, it's a family. I have also observed that for certain problem classes, certain functions work better than others. And certain don't work entirely. So like I'm saying, I don't know why it works, but I know it works. So.
Right. Well, thank you again. And thanks to everyone who joined us. Let's stop the recording.
All right. Thank you, everyone. You have a question? No.
Thank you.
Thank you.
Then there's one more thing. Yeah.